Hello? Hello?
And then it was 4 true, 4 false for that organization. Yeah, I did a good check.
Yeah, I was going to say. Listen, there's nothing wrong with that. Hello? Hello?
He's here to help us. Why would you miss that?
All right, let's get started. So I think what I'm going to be doing today is homework problems. This is what I was assigned to do. So we'll be going over select homework problems. Live stream is up. This is recorded. I think since we already have a lot of you know that the homework answers to the problems that we graded are on Canvas, right? Just to make sure that everyone knows that's on Canvas. So those are on Canvas, and then recitation 7 and recitation 8, so that long-ass spring break homework is also on Canvas with solutions to all of those. So I would highly recommend taking a look at those solutions. I'll go over a few of them today in the regular homeworks, and then I was thinking about maybe doing like a crash course at the end of just the relevant topics for the midterm. So what I did in previous semesters was that I would actually take a recitation just to go over a cheat sheet. But since we're really not allowed a cheat sheet, maybe I'll do the same thing, but it'll just be a high level overview of all the topics you need to know for the exam. Okay, so that's gonna be the goal. We're gonna do some problems, and then we're gonna go over the high level overview again. All this is being streamed, all this is being recorded right now, and so I'll upload everything. It should be online by the end of tonight. Yeah, a few hours after we're done here. Okay, so let's jump in right away then. And first problem, so we're going to start with the older homework problems, and we're going to jump to the newer homework problems. So we're going to start with homework 4. And so let's talk about number 5, which is the following. Consider V is equal to f mapped from the reals to the reals, and f of x is equal to c1x. So my computer screen, like this top right corner, I actually broke. As you can see, I can't write up there. So that was not a good spot to be putting this problem. F of x is equal to c1x plus c2 divided by x minus 1, x minus 2 for some c1, c2 in R. Okay, part A is show that V is the subspace of all functions. That's fine, let's skip that one. Part B is one basis for V. So one basis is B is equal to 1 over x minus 1, x minus 2. And the other basis is x over x minus 1, x minus 2. And then a basis C is equal to 1 over x minus 1, 1 over x minus 2. And we want to find the change of basis matrix then, P from B to C. Okay, so the important question here is then, all right, so when we have a change of basis matrix, it's really tempting, right, to try to put this into some augmented matrix here and say this is C, this is B, and then try to reduce it, right? So in general, this should work. And then once we reduce it to identity matrix on the left-hand side, we have P from B to C on the right-hand side, right? And notice the way we put it in this way is that B is on the right, C is on the left. But why doesn't that work in this case? Why can't we just put it in, yeah.
Does one of them have to be the standard basis?
So does one of them have to be a standard basis? No, not even that. No, they don't have to be a standard basis, actually. Yeah, there's just no good way to write those bases in like a vector form, right? So like for polynomials and for like vectors, it's pretty easy just to like eyeball like what the columns are supposed to be. Here, like what are we really supposed to put in for C, right? I mean, we have, so that's an x minus 1, x minus 2, looks really bad, right? But like what are supposed to go in the columns here, right? It's not immediately clear. Like if you put 1, 0, 0, 1, and like then you're like done, but that isn't the correct change of basis matrix. So we actually have to do this the normal way then of finding change of basis matrices. So P from B to C is equal to, right, some matrix where okay, and now we need to write this always takes me a while to figure out, right? Which vectors do we need to write in terms of which bases? Yeah, we need to write B in terms of C, okay? So here we need to write, let's say, like B1 in terms of C, and we need to write B2 in terms of C. Okay, so in this case then, all right, so B1 we need to write in terms of C, so let B1 equal 1 over x minus 1, x minus 2, and B2 equal x over x minus 1, x minus 2. Right? And so what is this? What is B1? Well, if we just find linear combinations of C, right? So now C, let's say C1 is equal. Okay, I don't like that notation there. Let's call it v1 is equal to 1 over x minus 1, v2 is equal to 1 over x minus 2. So I just have the basis for b written here. And these are the b basis, and these are the c basis. So let's just see what a linear combination of c gets us, right? So if we do c1 over x minus 1 plus c2 over x minus 2, we'll get c1 x minus 2 plus c2 x minus 1 divided by x minus 1 times x minus 2. All right, so we just complete the denominator to get a like denominator, and then we add them together. And so we'll get, and so now we want to find c1 and c2 in order to give us what b is. Okay, so we want to write b1 in terms of c1 and c2. So b1 is, so the denominator is going to stay the same, right? So notice how all these denominators are the same. So we just need to match the numerators, right? So the b1 is equal to the numerator of b1 is equal to 1, and that's going to be equal to c1 x minus 2 plus c2 times x minus 1. Okay, and does anyone see a combination of c1 and c2 that would be able to get me 1 in the numerator? Yeah, minus 1 and positive 1. Right, so if I let c1 equal negative 1 and c2 equal 1, then I'll get 2 minus x plus x minus 1. And so the x's cancel, and that's going to be 1. So b1 is equal to negative 1, 1 in basis of c. Okay. What's the next step? All right, so now we got to do the same thing for b2. So the numerator of b2 is equal to x, which is equal to c1 x minus 2 plus c2 x minus 1. Okay, and now what is a c1 and c2 that can get me the desired? Yeah, negative 1 and 2. So if I get negative 1 x minus 2 plus 2 times x minus 1, that's equal to, and then 2 minus x, wait, negative 1 and 2, plus 2x minus 2. And so the 2 and negative 2 cancel out, and you get just positive x. All right, so then b2 is equal to negative 1, 2 in terms of basis c. Okay. Now, next step. So, here's my problems. Homework, homework, homework. Okay, so now we throw this in. We have b1 and b2 in terms of c. So pbc is equal to negative 1, 1, negative 1, 2. Okay. Any questions so far? Yeah.
When you had c1 over x minus 1 plus c2 over x minus 2, where did that come from? And like, how did you...
Yeah, so this is a linear combination of the c bases.
So did you just take like c1 and c2 and multiply it?
Yeah, by the basis elements of C up there. Yeah, so that's because we want to write basis B as, like, the B vectors as a linear combination of the C vectors, right? Because that's how we get the coordinates of C. Okay. And okay, what's the next part? The next part is using the fact from part B, now compute these integrals, right? So part C is compute the integral of a over x minus 1 plus b over x minus 2 dx, which is equal to a log absolute value x minus 1 plus b log absolute value x minus 2 plus c. All right. And so now we know we want 2x plus 1 over x minus 1 x minus 2 dx. Okay, so how are we going to convert this into one of those matrices? Yeah.
Multiply the vector by the change of basis, like the p.
Yeah. Okay, so what we have here is that this vector is written pretty clearly in terms of the b basis. So if we go back up to the b basis, right, it's 1 and x over x minus 1 and x minus 2. So here, it's just a linear combination, right, of 2b1, or is it 2b2, right? Yeah, 1 plus 2b2. 1b1 plus 2b2. Okay? So really, so now we want to use the fact that the vector in terms of basis C is equal to P from B to C times the vector in terms of basis B. Okay, and so in basis B, this vector, okay, so let's write our change of basis matrix down first, negative 1, 1, negative 1, 2, and then this vector was 1, 2. Okay, and so that will get me the vector then in terms of basis C. And so now, doing this multiplication, we see that the vector here is going to be negative 3 and then 5. Okay? And so 3 is the coefficient in front of v1, and 5 is the coefficient in front of v2. So if we go back up here for v1 and v2, right, v1 is x minus 1, v2 is x minus 2. All right, so v1 was 1 over x minus 1, and v2 is 1 over x minus 2. Okay, so now this integral really becomes, right, here's v1 and here's v2, and now we know the coefficients in front of v1 and v2. So this will be 3 over x minus 1, negative 3 over x minus 1, plus 5 over x minus 2 dx, and then we just plug those numbers into that integral up there. So we'll get, so this integral is equal to this, and then which is equal to log, negative 3 log x minus 1 plus 5 log x minus 2. And then plus some constant. Okay, any questions? And then you do the same thing for the other integral. It's the exact same calculation, just different numbers. Okay, so why would I talk about this problem? The reason why I want to talk about this problem is mainly because of the change of basis matrix up here, especially knowing how to write the change of basis matrix in a general form. So that definition there is really important to remember because it's not always going to be the case where your change of basis matrix is going to be easily reducible by an augmented matrix. Okay, so that's the reason why I wanted to talk about this problem, is know how to set up the change of basis matrix in general if you can't set it up with just a simple row reduction augmented matrix. Okay, any questions? All right. Next question. Number 11. So same homework, homework 5, number 11. Okay, and it's consider the set V is equal to F from R to R, and F such that F double prime minus F is equal to 0. So in other words, this is the solutions to the ODEs, right? I.e. solutions to the ODE, F double prime minus F is equal to 0. So now that we've actually begun how to do ODEs, this problem is actually super easy to do, right? Now that we actually know how to do second order ODEs. So part A, we're going to skip because it's to show that these elements are they give you like e to the negative x, and you want to show that that's in V, but all you do is just plug that in for f, right? So you take two derivatives and then you subtract f itself, and then you just show that that's equal to 0. Okay, that part's easy. Part B, show that the vectors, all right, either the x and either the negative x are linearly independent. And there's also like cosh and sinh in this problem, but let's just ignore those for now because you probably won't have to worry about cosh and sinh on an exam. Or I really hope you don't need to worry about cosh and sinh on an exam. So how do we show that these two vectors are linearly independent with functions? The Wronskian, right? So the Wronskian, in this case, it's equal to, all right, e to the x, e to the minus x, all right, and then we just keep on taking derivatives, right? So what's the derivative of e to the x? E to the x, and what's the derivative of e to the minus x? Yeah, minus e to the negative x. Okay? So the Wronskian is equal to, and, okay, so when you have solutions to an ODE, you can't plug in points for the Wronskian. All right? What you want to do is you actually want to just solve this Wronskian out. And when we talk about certain other methods for solving diffie-qs, it's the same idea. Just actually calculate this Wronskian. So what we have now is we got negative, okay, so we got e to the x times negative e to the x. Or, yeah, e to the x times negative e to the negative x minus e to the x times e to the negative x. All right, so what is this going to get us? This is going to get us, so e to the x minus x, that's e to the 0, right? And so that's 1. And so what this is actually going to be negative e to the x minus e to the x minus x. All right, because you add the exponents, and now what do we get? We get negative 1 minus 1, which is equal to negative 2. So the Wronskian is equal to negative 2. Does that tell us anything? It's not 0 anywhere. Okay? So not 0 for every x. Right? No matter what x we choose, no matter what x we plug in to e to the negative x, we're just going to get 2 as a Wronskian. Okay? So since it's not 0 for every x, this is linearly independent. All right? And this is the chapter 8 Wronskian interpretation. So I talk about this in my recitation video. I'm not sure if the other instructors got to it, but I do compare the chapter 4 Wronskian and the chapter 8 Wronskian in my recitation, if for those in my recitation, if they recall. So it has to be not 0 for every x. If at any point it is 0, then it's actually linearly dependent. All right, so if there's a single point where that is equal to, where the Wronskian is equal to 0, we actually have linearly dependent solutions to the ODE. Okay, any questions? All right, part C is the following. Okay, show that, okay, so part C just tells you that, let's just say that C, e to the x and e to the minus x is a basis for V. Right? So essentially, those two are solutions, right? They're a basis for the solution space to the differential equation f double prime minus f is equal to 0. Right? That's all it is. We can actually find this now, right? With our tools, we know just to factor it, and we actually can find these two solutions. So now, part D asks us to find the initial value condition, u double prime of x minus u of x is equal to 0, u of 0 is equal to 5, and u prime of 0 is equal to 2, or negative 2. All right, so the initial value problem is something that you will need to know how to do for the exam, and we just introduced it, I guess, 4 homeworks early here, just to give you exposure to how to do this, how to actually do this. Okay, so right, we can write this in terms of derivative operator and find the kernel of L, but we already have the kernel of L, right? It's e to the negative x and e to the x up there. So we know that the general solution, right? So the kernel of L is equal to this basis right up here, right? E to the x, e to the negative x. So what's our general solution? Well, our general solution is u of x is equal to a linear combination of the kernel elements, right? So C1 e to the x plus C2 e to the minus x. Okay? But if you're given initial conditions, like up here, you can't leave your answer like this. That's like half credit, all right? If you have initial conditions, the reason why we give you initial conditions is to actually find what C1 and C2 are. So now what do you want to do? You actually want to try to find the initial conditions. So you know that you have this u prime, and so what we need to do is we actually need to take the derivative then of u of x. So let's just do that now. U prime of x is going to be equal to, well, what's the derivative of e to the x? It's just e to the x, right? So this first term stays c1 e to the x. All right, and now the second term, if we take the derivative of e to the negative x, right, that negative sign comes down, and so now we're left with minus c2 e to the minus x. Okay, and now what? Well, we know u of 0. Okay, so we plug in 0 into this x here, right? We plug in 0 into those x's, and we see that that just becomes c1 plus c2, because it's e to the x, right? So e to the 0, which is 1, and then e to the minus 0 is still 1. And we know c1 plus c2 is equal to 5. That's given to us in the initial conditions above. And now u prime of 0, that's going to be c1 minus c2, and we know that's equal to negative 2. Okay, here we got a system of 2 equations and 2 unknowns. So now we just need to solve for c1 and c2. And I think, I'm not sure entirely what it's going to be. C1 looks like 3 halves, and C2 looks like 7 halves. Okay. So now we know what C1 and C2 are, and we need to plug them back into the original u. So u of x is equal to 3 halves e to the x plus 7 halves e to the negative x. And so this specific solution will get us the initial value conditions given in the problem. Okay, any questions? So this kind of initial value problem, you should expect to see. Or actually, it's fair game, I would say, for the exam. I don't know. So generally speaking, like, if we just give you a really simple ODE to like factor and solve, that's like almost like too simple for 10 points, right? So what do we have to do to give you, like, to like allow for more error, I guess, is we'll give you some initial valid conditions, and then you have to solve for this constants. Okay. I clicked on something else again. So I think that's it for homework 5. No, that was from homework 5 as well. I just misspoke. Yeah, they're both from homework 5. So this is from homework 5. All right, so we'll move on to homework 6. Okay, so for homework 6, let's talk about number 4. All right, so in this problem, V is a vector space of 2 by 2 real entries. So V is a vector space of, it's really M2 by 2, or M2R. Okay, and then you have a map T that takes you from V to R. Okay, and then T of A, B, C, D is equal to A plus D. So in other words, T of M is equal to trace M for some matrix M. All right, part A is to show that T is a linear transformation. Okay, so what are the criteria to show that T is a linear transformation? Close under addition, close under scalar multiplication, right? So let's look at addition first, right? What do? We always choose general elements of our input, right? Take 2 general matrices. Can't read that. In M2R. All right, and we add them. So now we have to do, so let's take A, B, C, D, E, F, G, H, right? And so we want to show that T of A plus E, B plus F, C plus G, D plus H is equal to T of A, B, C, D plus T of E, F, G, H. Okay, so what is T of A plus E, B plus F, C plus G, D plus H? Yeah, so it's the trace of that matrix, right? So it's A plus E plus D plus H. All right, so what can you do now? Well, we can mess around and we can just rearrange some terms. This is A plus D, and then this is plus E plus H, so I kind of just flopped these 2 terms in the middle. All right, well, A plus D is what? Yeah, trace of A, B, C, D, so T of A, B, C, D. And then E plus H is T of E, F, G, H. All right, and so that's good. Scalar mult. Take a constant in R and then 1 general matrix in M2R. All right, so now we want to show that T of Ka, Kb, Kc, Kd is equal to K times T of A, B, C, D. And then T of Ka, Kb, Kc, Kd is equal to Ka plus Kd which is equal to k times a plus d, which is equal to k times t of a, b, c, d. All right. Part B is to find T, B, C, where B is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Right, so I'm just putting ones where that's not 0. And then C is equal to 1. Okay, so how do I find TBC? Well, if you remember, TBC is equal to TBE times PEC. Or another way to do this is to say that TBC is equal to the matrix where you apply T to V1 and you express it in terms of basis C, T applied to V2, and you express it in terms of basis C, etc., etc. Right, so those two are equivalent. And in this case, V1, V2, they're the basis B. Okay, so what's the catch? Well, the catch is, what does this turn into if B and C are both the standard bases? Or if C is just the standard basis for the output vector space? Right? Well, if C is E, right, this is the standard basis for the output space, then you get PEE times TBE. But what is PEE? It's the identity matrix, right? So that's just equal to TBE, which is just equal to T of V1, T of V2, etc., without needing to change coordinates. Right, and the same thing, V1, V2 are the bases of B. Okay, so let's look at our map back up here. Right, T is going from V to R. What is the dimension of R? 1. What is the standard basis for R? 1, right? So in this case, what is C? Well, C is 1. So C is the standard basis for my output space, right? So I don't have to do any change of basis crap, right? I can just straight up plug in the basis elements of B, which are V1, V2, right? They're in B. I just plug them into the map, and then that will spit out the transformation matrix for me. Okay, so let's do that then. So in this case, TBC, right, is just simply TV1, TV2. Okay, and so what is this? Well, what is T of V1? So V1 is going to be the first basis element here. That's V1. T of 1, 0, 0, 0. What is that equal to? 1, right? It's the trace of that matrix, so it's 1. Okay, and so we put it in the column. That's it. All right, what's T of V2? So this is TV1. What's T of V2? 0. What is TV3? 0. What's TV4? 1. All right, any questions? Yeah.
What would be a non-standard basis for R?
Literally anything that's not just 1.
And so,
Like any number.
so if that was other numbers, could you factor it out in a way?
Yeah.
Okay.
You have to write like everything in terms of like a multiple of that number. So it's kind of bizarre, but I wouldn't worry about non-standard bases for 1-dimensional spaces. Worry about them for like 2-dimensional spaces and above. Oh, okay. All right. Any other questions? Yeah, so this one, not too bad, I hope. Let's see. Oh, okay, and so, I mean, we should probably check that the dimension of this matrix is correct, right? And if you remember, so if we go back up here, the map goes from a dimension 4 vector space to a dimension 1 vector space. So T should have been a 1x4 matrix. And in our case, that is true. All right. So yeah, and this is a 1x4 matrix. So everything is good. All right. Part C is what is the rank of this matrix and what is the nullity of this matrix? What's the rank? 1. What's the nullity? 3. All right. Okay. Let's see. Let's talk about number 5. So this was the one where like VI was equal to cosine 2 pi over 7I, sine of 2 pi I over 7. And then T was from R2 to R2. And you want to show that T of V1 plus all the way up to V7. Oh, so you know this is true. Sorry, you know that it's linear. So now we want to show that V1 plus V7 is equal to the 0 vector. Yeah, is equal to 0. Oh, TR2R2 is rotation. Counterclockwise. Phi, 2 pi over 7. Okay, so any ideas on how we do this problem? Yeah. So use the standard basis in R2 and then what afterwards? Do a change of basis. So I don't think we actually even need to do any like calculations. This is more of like a theoretical problem. Yeah.
You just say because it's 2 pi over 7 times 7 is 2 pi, so you end up where you started.
Right, okay.
Is that enough?
Yeah, so if you know that okay, yeah, so that is what you want to that is enough, right? So if you rotate everything by 2 pi over 7, you are just going to end up where you started, right? So what does that mean? So since every vector just got rotated by 2 pi over 7, you know that wait, okay, so how did I want to phrase this problem? So this guy right here is rotating all the vectors by 2 pi over 7, right? And it's the same thing as like, okay. I should know how to explain this. You know that, okay, you know that you want to talk about the kernel of the map in some way. Okay, yeah, so we know that this is going to be is every vector rotated by 2 pi over 7, and if you add that all up, you should get that this is equal to 0. Right? Yeah.
Can you also say that because TV1 is V2, TV2
Yeah, okay.
TV3 is V4, and then T7 and TV7 is V1.
Right.
So it's basically V1, T of V1, V2, V3, V7 goes to V1 plus V2. So it's not rotating by any amount, so that has to be the 0 matrix.
It's the 0, right. So everything just ends up being the same.
Yeah, so it's the 0.
Right? So it's the, well, it's not the 0 matrix.
It's the 0 vector.
It's the, yeah, it's the 0 vector,
Yeah, so
right?
The only vector that's the same after rotation is the 0.
Yeah, exactly. So, right, so we know that after rotation, right, so after we rotate everything, everything stays the same, okay? That's what's going on right now. So the only vector, right, that after rotation that stays the same is the 0 vector, okay? So what we're really making is an argument for the kernel, and that the kernel has to be the 0 vector, right? Because if you think about it, if T is a rotation matrix, right, and T of V1 is the same thing as, so T of V1, V2 plus V7, this is the same thing as V1 plus V2 plus V3 plus V7. Right? Because you're rotating each vector, you're just moving each vector over counterclockwise. Okay? So you know this is the case, and so now what you know is that, well, the kernel of T, right, is the trivial vector. Because the only vector, right, that gets rotated to the 0 vector, just think about rotation matrices, right, everything has to get moved. So the only vector that's going to stay in the kernel is going to be the 0 vector, right? So the 0 vector gets rotated to the 0 vector. Okay, and what do we know about V1 plus, so now we know that, okay, the only vector that gets fixed ever, right? Because essentially what's happening is that you're rotating some vector and it's staying fixed, right? So T of V1 plus V7 is equal to V1 plus V7. So V1 plus V7 is fixed in the map. Does that make sense? V1 plus V7 is a fixed point in the map, and the only point that we know in T which will be a fixed point is the kernel. Yeah?
So the question is asking us to find a kernel of the map.
No, what we need to use the kernel to show that this is true, right? Because the kernel, right, this is T of, so any vector in the kernel is TV is equal to 0, right? That's the definition of the kernel, right? Is TV is equal to 0. But since we know that the kernel is the trivial kernel, what does this V have to be? 0, right? Since the kernel is trivial. So then, so this has to be T of 0 is equal to 0. So we see that 0 is a fixed point of the map. Right? But what else do we know? We know V1 plus V7 is a fixed point.
Can you
you also approach this by like, the rotation matrix of 2 pi over 7 is like, cosine, sines, negative sine, cosine. Could you just make those linear, like show that they're linearly independent, so that the only thing that's in the kernel is 0?
So I mean, here we're just stating that the kernel is 0 of a rotation matrix, right? So you would just be formally showing it in that case, which you don't have to because you can just state that the kernel of a rotation matrix is going to be 0. But so we know that 0 is a fixed point, and we know that v1 plus v7 is a fixed point in the map, right? Yeah.
I know this isn't like pertinent, but like could your linear transformation just be like nothing, where it like moves it from it to itself? Like say it's like
Yeah, so the identity transformation.
Yeah.
Uh,
But we know it's not here because it says it rotates it by 2 pi.
right, exactly. Right, so it's not entirely the identity matrix. I think if you actually write this out in terms of like a basis, it would be like a shifted identity matrix almost, but not quite. But in any case, what we're trying to point out is that v1 plus v7, right? v1 plus v7 is a fixed point. T of v1 plus v7 is equal to v1 plus v7. T, the kernel of T is trivial. So 0 is a fixed point. Since v1 plus v7 is a fixed point and 0 is a fixed point, then so v1 plus v7 is equal to 0 since we know that they're both fixed points. And why isn't there another fixed point in the map? Right? Why aren't there other fixed points in the map of rotation? I mean, one way is just like, think about it. We're rotating vectors, right? So every vector is just going to get rotated, right? But the only vector that's not going to get rotated is the intersection of the xy point, right? So that's like the only point that's not going to get rotated. So another way to think about it is that rank of T is equal to 2. Yeah.
Is that line of like the node, is that whole line given to us, or do you have?
So this is given. This is given.
But isn't that just like, you know that because like you have the closed
Yeah, this is given to you, but you know it anyways because it's closed under addition, right? This is what you had to deduce. Because you're shifting everything over, right? You're rotating, like imagine you have 3 axes, right? And you're rotating everything by pi over 3, right? But it's the same 3 lines. But here you just have 7 lines and you're rotating everything by 2 pi over 7. So it's going to be the same 7 lines.
But aren't there
It doesn't matter because right, T1 goes to T2, T2 goes, V1 goes to V2, V2 goes to V3, V3 goes to V4, V4 goes to V5, and then V7 goes to V1, right? So that's the hard part. And then I guess this rank argument isn't technically correct, but why are there no other fixed points? Because the rotation is not like 2 pi, right? If the rotation were like a 2 pi rotation, then everything would just be the same thing. But in this case, it's not. So you had to see that v1 plus v7 is a fixed point, and then the kernel is the only other place where there's a fixed point of the map. Okay. Any other questions? So this one's like a conceptual problem. It took me a while to figure out how to explain it, but I think use this fixed point argument to explain that. Okay. Another problem on here was number 10. Okay, so this one's actually the one on the previous exam that he gave you. And from what I understood, I didn't TA for Professor McGrath last semester. This problem was complete carnage on the exam. So let's take a look at it now. So consider the transformation T from U22 to U22. All right, so it's the space of upper triangular 2 by 2 matrices. Okay? And T of M is equal to 1, 2, 0, 3 inverse M 1, 2, 0, 3. Let A be the C matrix of T. So I guess like the notation isn't great. So let A be the C matrix of T, which is really TCC. Okay? So that's what that really means. And B be the B matrix of T, which is TBB. All right, and P equal the change of basis matrix, PBC, B2C. All right, so now what? Now I need to give you the bases. So C is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and B is equal to 1, negative 1, 0, 0, 0, 1, 0, 1, and 0, 0, 0, 1. Okay, part A is to find A and B. Right? So in other words, find TCC and find TBB. Okay, so how do we do this? Well, right, TCC is equal to T of C1 written in basis C, T of C2 written in basis C, and T of C3 written in basis C as well. All right, but what is C? It's the standard basis for what? Upper triangular matrices. All right, so C is standard basis for upper triangular matrices, and that's important to recognize for this problem. All right, C is a standard basis for upper triangular 2 by 2 matrices. Okay, so really, I don't have to write subscript C here. It's just plug C1 and C2 into the change of basis. All right, so this is really just TC1, TC2, and TC3. All right, the only annoying thing is that we got to do all this multiplication. So first of all, let's try to find what 1, 2, 3 inverse is. And that's equal to 1/3 times 3, 1, negative 2. Okay, so what is TC1? TC1 is equal to 1, negative 2/3, 0, 1/3 times 1, 0, 0, 0 times 1, 2, 3. Okay, and so that's equal to 1, 0, 0, 0, I believe, times 1, 2, 0, 3. Now this is equal to 1, 2, 0, 0. Okay, what's TC2? Same thing. Right, but now we plug in 0, 1, 0, 0, 1, 0, 0. And so what is this? 0, 1, 0, 0. Okay, so it's the same thing? No. 0, 1, 0, 0 times 1, 2, 0, 3. And that's equal to 0, 3, 0, 0. Okay, T of C3 is equal to 1, negative 2/3, 0, 1/3, 0, 0, 0, 1, 1, 2, 0, 3. And so the first multiplication is 0, negative 2/3, 0, 1/3. Times 1, 2, 0, 3. And so that gets us 0, negative 2, 0, 1. Okay, so what goes in the first column of T? 1, 2, 0, right? We're doing upper triangular matrices, so read off the upper triangular entries. Like that, all right? So you read off this entry first, this entry, and then that last entry. That's the order that were given to us in the basis, okay? Top left, top right, bottom right. And so here I do top left, top right, bottom right. Okay, what's the second entry? 0, 3, 0, and what's the last entry? Great. Okay, so now what's B? The B matrix, well, that's equal to TBB, which is equal to T of B1 written in B, T of B2 written in B, T of B3 written in B. Okay, and what is B? Remember, B is 1, negative 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, and 0, 0, 0, 1. Okay, so let's find what T of B1 is. And remember, the other way we can do this problem right here is we can find P from, we can find the change of basis matrix from E to B, and then just plug in T of BE, right, and multiply that by T of BE. These two are equivalent ways of going about finding the matrix. But anyhow, we need to find what T of B1 is. So T of B1 is equal to 1, 2, 0, 3, 1, 0, negative 1, 0, or that inverse. So let's just write it in. 1, negative 2/3, 1/3, 1, negative 1, 1, 0, 1, 2, 0, 3. Okay, and what do you get? You get 1, negative 1, 0, 0, 1, 2, 0, 3, and then you get 1, negative 1, 0, 0. So you get the same thing. T of B2. You get 1, negative 2/3, 0, 1/3, 0, 1, 0, 1, 1, 2, 0, 3. And so there's a reason why McGrath actually chose these two matrices, is because you actually get themselves back once you conjugate. So this is actually also 0, 1, 0, 1. Okay, and the last matrix is T of B3, but B3 is the same thing as C3. It's the same matrix. So T of B3 is equal to 0, negative 2, 0, 1. Okay, so now what? Now, right, we want to write each one of these matrices, each one of these output matrices, as a linear combination of the B basis vectors. Right? So we want this to equal K1 of, well, the B basis, which is 1, negative 1, 0, 0, plus K2 times 0, 1, 0, 1, plus K3 times 0, 0, 0, 1. Right? Because these are the B basis vectors. So what is a triple K1, K2, K3 that gets me 1, negative 1, 0, 0? Just 1, 0, 0, right? Because I literally, this 1, negative 1, 0, 0 is literally the first matrix in the B basis. All right? So in this case, that's 1, 0, 0. Okay? So 1, 0, 0. Okay? What about 0, 1, 0, 1? I also want to write it as a combination of these three guys. Yeah, 0, 1, 0. Okay, so this is TB1 of B, and this is TB2 of B. All right, and then what's the third one? Well, the third one, a little more tricky to eyeball, but shouldn't be that bad. So one way we can do it is we can say, okay, right, we can unravel these matrices into column vectors and write a system. So 1, negative 1, 0, 0, right? Well, it's upper triangular, so I don't even need a... It's upper triangular, so I can even ignore the bottom left entry. Right, so this is 1, negative 1, 0, 0, 1, 1, 0, 0, 1 is equal to 0, negative 2, 1. Right, and so this would be the K1s, this would be the K2s, and this would get me the K3s. And so this shows that K1 is equal to 0, right? Because I got 1, 0, 0. So K1 is equal to 0 from row 1. And then from row 2, I see that K2 is equal to negative 2. Just straight up, that's what it says. Right? And then in row 3, it says K2 plus K3 is equal to positive 1. Right, so that's what the three rows are telling me. And, well, what does that mean? Well, this means that K3 is equal to positive 3, right? Yeah.
Isn't the third basis vector 0, negative 2, 0, 1? Or like, I mean, obviously you take out the bottom left, but like, isn't it 0, negative 2, 1?
No, but no. This is T of B3. Is equal to that guy.
Yeah, but I thought you said
but
that.
B3 is that guy, 0, 0, 0, 1.
Oh, okay.
Right. Like if we look at the basis vectors given to us, right, B3 is 0, 0, 0, 1.
Okay.
Yeah. So that's why it's fine. Okay, and so now the last vector is going to be 0, negative 2, 3 that we put in. And so there we go. Okay? And so this is our answer for part 1 of the problem. Yeah, now that I think about it, this is a really long problem for an exam.
How long do they have to do this? 50 minutes or an hour?
I think they have 50. Okay. What's part 2? Yeah, part 2 is state a known relationship between A, B, and P. And remember, A is TCC, B is TBB, and P is the change of basis matrix B to C. Right? And so what might be useful here? What should we also just write down? Well, okay, so it looks like we want to go from one of the matrices to the other matrices, right? We want to go from A to B or B to A. So we might want to find, so we also know that P inverse is equal to P from C to B, right? The inverse of a change of basis matrix is the change of basis going the other direction. Okay, so now what? So now we can say, all right, A is TCC. So we got TCC is equal to, right, TBB in the middle. All right? And then you got P from C to B, right? And then let's say you got P from B to C, right? Because the idea is you start your journey in C, you go through all these B guys, right? And then you end up back in C, right? And that's what we're doing here. We started in C and we end up back in C. Okay? And so what is this? Well, this is, well, TCC is A, PBC is P, TBB is B, and that's B inverse, P inverse. So this is actually an exercise in like similar matrices. So that's part 2. And then part C is just to like actually just multiply out the matrices and make sure that they work. So, and it works that way, yeah.
So why do you have to write this relationship in particular? Because by this point we hadn't done diagonalization. Could we write like A?
Well, this isn't diagonalizing, is it? I think this is it's similar matrices. So it's not. So, well, yeah, we still didn't know the definition of similar, but it's just to motivate the idea. Well, on the exam, like they had covered similar matrices and like whatever by that point. So on the homework, this is like a little more rough to figure it out at the time, but it's also to motivate like in the future, like what we're going to talk about and how like change of basis matrices relate to the process of diagonalization or similar matrices.
Okay.
Okay, let's see. So this is still homework 6, right? All right. So since we graded the genetics problem in homework 7, let's talk about the genetics problem in homework 6 because it's like the precursor to the homework 7 problem. Right, so in this homework, you actually like use mathematics to compute the limit, and then in the next homework, you like diagonalize the matrix and then computed the limit using like SDS inverse. So in this problem, you have a little a little a little a little a little a. A little a, a. Okay, and then over here you had a little a, and then you got this 1 half, 1 half, 1 1/4, 1 half, 1/4, 1 half, 1 half, 0 0 1. Okay, and so you're told that each dog, I guess we're talking about dogs here, mate with the same genotype. So what does that mean? It just means that all these pairings on the top, they got to be the same thing. So ignore that, and ignore that. Okay, so that's the restriction on the problem. So what is part A? Part A is to find M such that x to the n is equal to m x to the n minus 1 for every n. And so, well, once you apply the restriction, your m is just reading off the columns that are left. And so you have m is equal to 1, 0, 0, 1 fourth, 1 half, 1 fourth, 0, 0, 1. Okay? And the idea is x is equal to some distribution of AA's, A little a's, and little a's. So there's going to be some proportion in there. Okay, and then part B, so part B is to just compute it using Mathematica and approach a limit. So let's actually just do this then using like diagonalization, right? So compute the limit as n approaches infinity. Right? So determinant of m minus lambda I is equal to 1 minus lambda, 1 fourth, 0, 0, 1 half minus lambda, 0, 0, 1 fourth, 1 minus lambda. Where's the absolute most easiest way to get this characteristic polynomial? Expansion where? Yeah, first column. So, or second row. I guess that works too. But you get 1 minus lambda times 1 half minus lambda, 1 minus lambda, 0, 0, 1 fourth. Right? And so this is a diagonal matrix, so you just get 1 minus lambda squared, 1 half minus lambda. So lambda equals 1 with multiplicity 2, and lambda is equal to 1 half. Okay, so lambda equals 1. You'll get 0, 1 fourth, 0, 0, negative 1 half, 0, 0, 1 fourth, 0. What's the rank? And what's the nullity? 2. All right. Is that a good thing or a bad thing? It's a good thing because algebraic multiplicity is equal to the geometric multiplicity. All right. So it's diagonalizable. So in particular, what is the span of the kernel? Yeah. 1, 0, 0, and 0, 0, 1. Okay, and now lambda equals 1 half. You get 1 half, 1 fourth, 0, 0, 0, 0, 0, 1 fourth, 1 half. Rank is 2. Nullity is 1. And what's the span of the kernel? Yeah, 1, negative 2, 1 should work. Okay, so A is equal to S ds inverse. Doesn't matter how you want to do this, but let's make D 1, 1, 1 half. And so A has to be 1, 0, 0, 0, 0, 1, and then the eigenvector for 1 half. All right, and then whatever this guy is inverted. All right. And then a to the n is equal to s d to the n s inverse. So this is a. So 1, 0, 1, 0, 0, negative 2, 0, 1, 1. 1 to the n is 1, 1, and then 1/2 to the n. 1, 0, 1, 0, 0, negative 2, 0, 1, 1 inverse. All right, and if we take the limit as n approaches infinity, right, this term goes to 0. Okay, so then the limit as n approaches infinity, it's you actually just multiply 1, 1 like 0, okay, and then you want to multiply this matrix out, and like this inverse shouldn't be that bad. We can do it, I guess. I guess it's a waste of time, but you should know how to compute inverses for the matrix. You should know how to compute inverses for the exam, because it's very possible that we'll actually ask you what a to the n is. Okay, any questions? All right. Homework 7. Okay, let's see, what should we... All right, let's do some of this true-false. 1a, if a, b, same characteristic polynomial, then a and b have the same lambdas. Is that true or false? True. Why is it true? Because how do we find eigenvalues? Well, we find it from the roots of the characteristic polynomial. So if they have the same characteristic polynomial, they're going to have the same roots, right? Roots of characteristic polynomial are the same. That's true. 1b, if ab have the same characteristic polynomial, then ab have the same eigenvectors. False. All right? Why is that false? Anyone want to give a counterexample? Okay. Exactly. All right, so usually with a lot of these counterexamples, try to think of like a diagonal matrix and then like the corresponding Jordan block. Like that's one way to find counterexamples. The other ways are just like think about like matrices with like a lot of zeros in them. Okay, part E. A linear combination of a set of eigenvectors is an eigenvector. That's true. All right? Yeah.
What if you take two eigenvectors with different eigenvalues? Because they literally
Right. Okay. So under different eigenvalues, it is false. Yeah. Under the same eigenvalue, it is true.
But then what do we?
So let's see. I would say this one then is false. So I was thinking under the same eigenvalue. Yeah. So you guys are right. So this is false because let's see if we can think of an example real quick. So when it's false, you can always get a counterexample. So maybe let's say like 0, 1, 0, 0. Lambda equals 0 is 1, 0, right? The eigenvalue, the eigenvector is 1, 0. And then for lambda equals 1, the eigenvector would be 0, 1. Okay? But is 1, 1 an eigenvector? No. Yeah. Yeah, so if they have the same eigenvalue, so if the problem asked is a linear combination of a set of eigenvectors for the same eigenvalue, right? Then you have a minus. All right, so let's say that v1 through vn are the eigenvectors for some lambda. All right? Then what is A times C1 V1 plus C2 V2 plus Cn Vn? Right? Because now we're taking a linear combination of all of our eigenvectors. Okay? Well, that's just equal to C1 AV1 plus C2 AV2 plus Cn AVn. Okay? Because you can distribute matrix multiplication. But what is AV1? Lambda V1, right? So this is C1 lambda V1 plus C2 lambda V2 plus Cn lambda Vn. And now what can we do? Take out the lambda. Right? So now this guy is equal to lambda times the scalar multiple of itself. Right? So it's true for the same lambda, but then if it's under a different lambdas, then it's false. Okay. Let's see. That's E. F. Okay, so I'm just going to say this. If a matrix has a repeated eigenvalue, then it's defective. False. All right? Diagonal matrix. The identity matrix, right? 1, 1 on the diagonal. Lambda is equal to 1, multiplicity 2. Right? But it's not defective. All right. All right, yeah, let's talk about I. If alpha squared has eigenvalue 9, then 3 or negative 3 must be an eigenvalue for A. So this one, I think we took off a bunch of points, mainly because there was like an assumption if you went one way. So I also didn't really want to grade this problem, but for some reason we ended up grading it. And the problem is not phrased too well. So here's the correct way we should have thought about doing it. So if we know that a squared has eigenvalue equal to 9, then we know that a squared v is equal to 9v. Right? What we can't say is that we can't just say, this is a no-go, AV is equal to some lambda v. Because what you're assuming here is that you're assuming that that same v is an eigenvector for A when it's an eigenvector for A squared. Okay? It's true. That's actually true, but you actually have to like prove it and then use it. Okay, so that's why this direction is like kind of not nice. All right, so you can't just say this is true, but you just can't do it like that. All right, because then you have to prove that if V is an eigenvector for A squared, then V is an eigenvector for A. All right, and so we've actually done variants of it, but I don't think we've like explicitly shown it. So how do you do it exactly? So the way you want to do it instead is the following. You move everything over to the same side. All right, so now you get A squared minus 9i times V. Okay? And you can factor this matrix. A plus 3i, A minus 3i times V. All right, and the reason why you can actually factor this matrix is because 3i is a diagonal matrix, right? So it actually commutes. Yeah. Okay, so now what? Now let's take the determinant of both sides, right? Or so now you can take. So there are two ways to do it, right? You can take the determinant of this guy, right? And you know the determinant of this is equal to 0. Right? You know the determinant of A squared minus 9 is equal to 0 because V is an eigenvector in the kernel, right? And so since there's a kernel for A squared minus 9i, then it's not full rank, so it has nullity, and so the determinant's 0. And so that means this determinant has to be equal to 0, right? So what does that mean? It means that either the determinant of A plus 3i is 0, or the determinant of A minus 3i is equal to 0. Okay? And if that's the case, then you know that you have an eigenvalue of 3. Okay, so that's like the way we wanted you to think about it. There's another way online where we actually consider the V, and then we like do some things there, but that's one way to think about it. And that's more of the correct way without like assuming that V is an eigenvector. Okay, let's move on to number 7. Okay, so number 7 is 2019, 2019, 2019, 2019, 2019. Right? And so there's 5 rows of this. Okay, so this problem tests pretty much everything in eigenvalue-eigenvector theory, and more importantly, it tests if you know how to use the lambda equals 0 condition. So, right? So what is the lambda equals 0 condition? The idea is the following. So this is an aside. The kernel of A is the same thing as the kernel of A minus 0i. Right? Because I'm subtracting 0 times the identity matrix. So that means, right? So that means the kernel of A, right, is the same thing as if lambda equals 0 was an eigenvalue. Right? It's the exact same thing. So that means that the dimension of the kernel of A, which is really the nullity of A, I can't spell, right, is the same thing as the dimension of the kernel of A minus 0i, right, for lambda equals 0. So this is like the lambda equals 0 case. So notice they're all the same thing. The top row is the same thing as the bottom row. So that means vectors in Ker A are eigenvectors for lambda equals 0. Okay, any questions? Right? And so what is the dimension of I forgot one thing. What's the dimension of the kernel of A minus 0I? Not the null. There's a more specific term I want. Not what the number is, like what term, because what multiplicity, what kind? Geometric multiplicity. Right, so the geometric multiplicity of lambda equals 0 is the same thing as the nullity of A. Okay, so this is A diagonalizable. That's what the question is. That matrix is A. Okay, so we start off, right, by saying, what is the rank and what is the nullity of A? Yeah, the rank is 1, right? So the nullity is 4. Well, that's the same thing as saying the geometric multiplicity of lambda equals 0 is equal to 4. All right, so let's find 4 eigenvectors for lambda equals 0, or 4 vectors in the kernel of A. All right, so what are 4 vectors in this kernel of all 2019s? So if you row reduce it, right, you'll actually just end up with 1s along the top and 0s everywhere else, right? Because I can just divide the entire matrix by 2019, okay? And so I'll get a matrix of all 1s, and then the last 4 rows just die because of the first row, okay? So you'll actually, like, after row reducing, you just get this, right, and then 0 everywhere else. And so now we need 4 vectors that span this kernel. And so one way to do it is, let's say 1, negative 1, 0, 0, 0, 1, 0, negative 1, 0, 0, 1, 0, 0, negative 1, 0, and 1, 0, 0, 0, negative 1. Okay, you can do it with free variables if you really wanted to. You can call this like x, y, z, w, and then, messed around with free variables, but or you can just eyeball it. And then this is a pivot. Okay, so I have 4 eigenvectors, right? So geometric multiplicity for lambda equals 0 is 4. So I have these 4 eigenvectors. Now, what do I want? Now the problem is, what is algebraic multiplicity of lambda equals 0? All right, and what are the possible values? So 4, any other? 5. Can it be 3? No. Okay. Can it be 6? No. Okay. So it can be 4 or 5, and that's because, and the reason why is because 1 is less than the geometric multiplicity, less than or equal to, which is less than or equal to the algebraic multiplicity. All right, and then this is less than or equal to n. Okay, so there are all these bounds on what geometric multiplicity and algebraic multiplicity can be. But in general, geometric multiplicity is going to be less than or equal to the algebraic multiplicity. So if I know this is 4, right, then this has to be 4 or 5. Okay, what would happen if the algebraic multiplicity of lambda equals 0 is equal to 5? It'd be defective, all right? Okay, so it'd be defective, so it would be non-diagonalizable, right? But can we have another lambda equals 0? Why not?
The trace is not 0, so
The trace is not 0, so that's the answer that's I'm looking for. Then the sum of lambdas, right, is equal to 0, plus 0, plus 0, plus 0, plus 0, which is equal to 0, right? But what's the trace of our matrix? Not 0. In fact, it's like 10,095, right? 2019 times 5. Okay? So lambda equals 0 can't have algebraic multiplicity equal to 5. All right? Which means algebraic multiplicity of lambda equals 0 is equal to 4. And what's the last eigenvalue? 2019 times 5. Okay, so is this diagonalizable? Yeah, because algebraic multiplicity equals geometric multiplicity for every unique lambda that we have. All right. Okay, any questions? Okay, so now what? Let's talk about homework 8. Well, this is actually the one due after the midterm. All right, I'm just thinking about what I should talk about that seems relevant, or we're not going to. No, I'm not going to do the bonus problem. All right, number 13. Let's do that one. Okay, A is equal to -1, -1, 0, 0, -1, -2, 0, 0, -1. Find S such that S inverse AS is equal to J. Okay, so since this is a diagonal matrix, we know what all the eigenvalues are. Okay, what are the eigenvalues? Yeah, lambda equals -1. Oh, it's triangular. Sorry, not diagonal. So for any triangular matrix, we know what the eigenvalues are. They're just the values on the diagonal. Okay, so multiplicity is 3, or algebraic multiplicity is 3. So if you look at lambda equals -1, I'll get the following 0, -1, 0, 0, 0, -2, 0, 0, 0. Okay? This is A plus I. Okay, what's the rank? 2, and so the nullity is 1. Right? And this is less than 3, so it's defective. So now what? So the next step is always to create your Jordan matrix. All right? Don't try to find S and whatever first. J, all right, is equal to -1, -1, -1. All right, and remember, what does the nullity tell us? Number of blocks. 4 lambda equals -1. All right, that's the important thing. It's just for this eigenvalue. Okay, so since there's only one block around my -1s, there's only one way to fill that in, which is 1, 1, and 0. Okay, so now we look at our S matrix, right? And what does our S matrix have to be? Well, each block corresponds to a cycle. So this block corresponds to 3 columns of S, and so this is a 3 cycle. All right, and how do we set up a 3 cycle? Well, we find some generalized eigenvector, right? That generates everything, and then we have A minus lambda I times the generalized eigenvector, and then we got A minus lambda I squared times the generalized eigenvector.
No, won't it be V and A minus lambda everything?
No, because multiplicity is 3, and you have 1 block. It's a 3 cycle.
Oh, yeah.
Yeah.
Can you go over quick how you get the cycle items?
Yeah. So the cycle, you look at the Jordan block, right? And it's a 3 by 3 Jordan block, and so since that Jordan block occupies 3 columns, that has to correspond to 3 columns of the S matrix. Okay. And then so now you have to be able to fill in 3 columns with a cycle. So you just start with V, your generalized eigenvector, right? And then you just keep adding powers of A minus lambda I until you have enough vectors. Yeah. So the algebraic multiplicity is 3, right? And the nullity is 1. Okay, so the nullity tells me the number of Jordan blocks corresponding to that lambda, which is lambda equals -1. And so the algebraic multiplicity being 3 just means that -1 occupies 3 spaces of the diagonal. Okay? And then so now I know that there's 1 block for all the lambda equals -1s. Right? And there's only one way to split that. Okay, so now what? So now remember, what's the conditions here? Well, the conditions is that VG satisfies A minus lambda I, and then you look at the power of your cycle, or you look at the length of your cycle, which is 3, so you got to cube that times VG is equal to 0. A minus lambda I squared times VG. Well, now this guy is in your matrix S, right? And what do we want to do with S eventually? Invert it, right? So I can't have like a 0 like vector in my invertible matrix, right? Because then it's not invertible. So that guy can't be 0. Likewise, A minus lambda I times VG cannot be 0 as well. Right, and that's because this guy goes here. Okay, so now what? Well, A minus lambda I was equal to 0, -1, 0, 0, 0, -2, 0, 0, 0. All right, let's find a basis for the kernel. Well, it's just 1, 0, 0, right? I don't know what I'm doing there. Okay, so the basis for the kernel of A minus lambda I is 1, 0, 0. A minus lambda I squared is going to be equal to 0, 0, 0, 0, 0, 0, 0, 2, 0. So the 2 in the upper right. And what's a kernel for this matrix? Yeah, 1, 0, 0, 0, 1, 0. All right, and then A minus lambda I cubed is actually going to be the 0 matrix. Okay, so the kernel, if you give me a basis for the kernel, it's actually 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. Okay, so remember, we need to pick VG that satisfies these conditions. So another way to think about it is we have to pick VG that's in the kernel of A minus lambda I cubed, but not in the kernel of any of the other matrices. All right, so VG in kernel of A minus lambda I cubed, but not any other matrix. All right, so we look at these kernels, and we look at A minus lambda I cubed, and now which vector inside of that kernel is only in the kernel of A minus lambda I cubed and none of the preceding ones? Yeah, so 0, 0, 1. So we got to choose this one. Right, so this is VG. Okay, and now what? So now, right, S is equal to 0, 0, 1. This was VG. A minus lambda I times VG is A minus lambda I times 0, 0, 1. So that takes the last column. 0, negative 2, 0. And then A minus lambda I squared is going to be 2, 0, 0. Okay, any questions? Okay. So that's Jordan canonical form, and I think that's about it. So I think we're running out of time here. So let me just make a few remarks about the exam in general. So I know we've been So I know a lot of you are like skimping on the calculations on the homework, which is fine, because I mean, who really wants to plug it do matrix multiplication of 3 by 3 matrices all day? But on the exam, you will be expected to do these multiplications and to do these calculations, and you will be expected to do them correctly. I mean, if one thing, just be able to do calculations on the exam, actually just go through the grunt work of some of these problems, stuff like finding the characteristic polynomial and stuff like that. You might run into something where you have to factor a cubic or something along the lines of that. So just prepare for those things. Again, those are all just implicitly assumed that you know how to do. And I told my recitations this, but if you can't calculate the characteristic polynomial of a matrix, you're gonna get 3 points maybe, and that's it, right? Because everything else is gonna be wrong. What else? I mean, spread is gonna be pretty equal starting from the chapters, so 4.7, which is change of basis, all the way through your ODEs. And I would again just definitely look at the solutions posted online the solutions are there. I don't know how detailed they are. When I took a look at them, they're okayishly detailed, but the problems that have solutions are probably the problems that are more fair game than the other ones. All of recitation 7 and recitation 8 homework is fair game since we put the entire solutions on there. And there's definitely going to be problems not on the solutions that are also fair game, but generally we'll put more emphasis on the ones that we think are important. Let's see. What else? In terms of recitation, recordings and stuff like that, I mean, I have a bunch of those online as well. It definitely won't hurt to go rewatch those recitation recordings. And I think in order, of the most important, recitation recordings, I think it'd be the Jordan canonical recording, and then just eigenvectors in general, and then the ODE recording, and then the linear transformation recording, and then the change of basis stuff. In that order would be the order of the recitations and the materials most important. I'd say these three here, there's really those are a wash. of like how important, like the amount of importance you should show of them. This thing though, it's just the hardest one, so I would just say it's the most important. It's just the hardest one to understand conceptually. These three are going to be all equally weighted on the exam. This one is also equally weighted on the exam. Again, it's just harder. And then this one, it gets implicitly tested in a lot of other questions. So, for example, diagonalization, right, is just change of basis matrix, TBB, change of basis matrix back to the original basis. So stuff like that. Again, all of this stuff is talked about, at least for me in recitation, I've talked about all of this stuff. So all of it's going to be fair game. Yeah. Couple ODEs? Oh, I know there's a, I should have done it. There was one problem that asked you to find the, solution to the system of ODEs, right? Yeah, I forgot to do that.
Maybe did that yesterday.
Maybe did it yesterday. I have an example in my recitation recording as well for a system of ODEs. You should know how to do those, so I would study those. You could get like a defective matrix. You could get like a non-defective matrix, right? I think the one on the homework is not defective. Did we grade that problem? It's homework 7, right? Yeah, actually, let's just do that one really quick, because I know there's no solutions written to it. Okay, so you got x prime is equal to x plus 4y, and y prime is equal to 2x plus 3y. Okay. So this thing is written in the form of x. So you can write this in the form of like x prime, y prime, 1, 4, 2, 3, xy. Right. So I just rewrote the system in terms of a matrix system. And so this is really the vector x prime is equal to some matrix A times the vector x. So x is equal to the vector xy. Okay. And now the idea is the system isn't really easy to solve. So choose a clever change of basis matrix S. All right, and so now let V equal S times X. All right, and the idea is the following. So we want to do Sx prime is equal to A times Sx. All right, so we just apply the change of basis matrix there. And now what we do now, x prime is equal to S inverse AS times X. Right? We move that S from the left-hand side over to the right-hand side. So this is what I mean by a clever change of basis of matrix S, because what can we make this thing? A diagonal matrix. But in general, if it's not diagonalizable, what can this thing be? A Jordan matrix. All right, so you choose some change of basis matrix that makes this either diagonal or Jordan, given what A can be, right? Because you can diagonalize A in this case, but sometimes you can't diagonalize A. All right, so this is really x prime is equal to Jx, but in this case, J is equal to some diagonal matrix. Okay, so I wrote, okay, so the terminology is just a little bit wrong here. This should be X is equal to SV, I think, and then V is equal to ASV inverse, and then just change the X's to V's. V prime is equal to JV. All right, sorry about that. So change that to V. Okay, and so let V is equal to, let's say, X tilde Y tilde. All right, and now what? So now you have this system V prime is X tilde prime Y tilde prime is equal to some Jordan form of SAS inverse times X tilde Y tilde. Right? But now we need to find what S inverse AS is. And in this case, I said it was going to be diagonalizable. So remember, A is equal to 1, 4, 2, 3. So A minus lambda I. Actually, so you find the eigenvalues. We can actually just eyeball them here if we really wanted to. Trace is 4. Determinant is -5. So it looks like 5 and -1. Okay? So then in the lambda equals 5 case, you'll get -4, 4, 2, -2. So this is A minus 5i. And so your eigenvector here will be 1, 1. And then in the lambda equals -1 case, you'll get 2, 4, 2, 4. So A plus I. And your eigenvector will be 1, -2. Okay, so in this case, right, D is equal to 5, -1, and S is equal to 1, 1, 1, -2. Yeah.
So V2 is -2.
Oh, yeah. Yeah, I can eyeball eigenvalues apparently, but not eigenvectors. Okay. Yeah, so that's S. And so now J is really D, right? Because S inverse AS in our case is a diagonal matrix. So then this is equal to, so we got X tilde prime, Y tilde prime is equal to 5, -1, X tilde, Y tilde. All right, and now we just multiply it out again. X tilde, Y tilde prime. So on the first row, you got X tilde is equal to 5 X tilde. So X tilde prime is equal to 5 X tilde, and the bottom you get Y tilde prime is equal to -Y tilde. So these are really easy to solve. Right? What is X tilde going to be? E to the 5, right? E to the 5t, sure, right? Because if you take the derivative, right, you get 5 e to the 5t. Okay, so that means X tilde is equal to e to the 5t, and Y tilde is equal to e to the -t. Okay? And then remember, V is equal to X tilde Y tilde, so that's equal to e to the 5t, e to the -t. Yeah.
Do you need like C1, C2?
Yeah, I think, yeah, you do. Yeah. It's not the end of the world if you leave it off on, like, the midterm. You'll miss, like, a point, but the problem's going to be, like, if this problem shows up, or something like this, like in general with an ODE, if you miss like the constants. I guess for an ODE, it's a little worse if you miss the constants because we might ask you the initial value problem, and then you need to know what the constants are. So then, yeah. So, but in general, if you're asked for a general solution, leave out constants. Not the end of the world. Yeah, but thank you for catching that. Right. So C1, C2, and then so that's C1, C2. Okay, and then finally, remember that x is equal to s times v, which is equal to 1, 1, negative 2, 1 times c1 e to the 5t, c2 e to the negative t. So that's c1 e to the 5t minus 2c2 e to the negative t, c1 e to the 5t plus c2 e to the negative t. Okay, so that's the system. The other way to solve it is to find the matrix exponential, but don't worry about it for this midterm. All right. Oh, but you do need to know how to find the matrix exponential in general, but don't worry about using the matrix exponential to solve systems of equations. Okay. Yeah. So that's gonna be it. I'm gonna a few minutes over. That's fine. If you want to pick up homework, I'll be in my office for like another 10 minutes or so, and then. This will be uploaded tonight, and I have office hours starting at 1 p.m. in my office all day on Monday. I'm just gonna sit there until we have to go meet McGrath to like pick up the exams and walk over to the exam room. So if you have any questions, last minute questions, feel free to stop by. Nibby's gonna be there as well. So yeah. So the cycle is the cycle
Yeah, probably.
So you have different. So for example, if you had, okay, you can see this pretty clearly, but if J was like a 2 by 2, and then like a 3 by 3, right? If this were J, then your S matrix is going to have a 2 cycle and a 3 cycle.
So it'd be like B and
Yeah. A minus lambda. Yeah, and then you start with a different B2 and then A minus lambda.
then, so generally our policy has been like this, 1 second.
Yeah. So on the in my recitation video, right, I think I do approach a problem where you have to like split up the cycle, where like it's not immediately clear what the cycle is. Yeah.
Thank you.
Yep.
Quick question, do you have a video on the most recent stuff that was talking about?
Yeah. So the chapter 8 ODE stuff is already on. This is like this is in his lecture notes. It's like one problem. Yes, a problem is I think it's like lecture 15. It's with diagonalization. So it's an application of diagonalization. And then he also has another example with the Jordan form. So here, this was diagonalizable.
Oh, but if it is, use the Jordan form.
Yeah, if it is, use the Jordan form instead. It's the exact same idea.